Hang in there, we're almost done. All right, so the last thing we're going to talk about is definite integrals using U substitution. And they're actually usually easier than indefinite integrals, and you'll see why we have less substitution to sort of less changes to make back and forth. So we have this kind of problem. We have tangent of x times the secant squared of x dx, and we're integrating as a definite integral from 0 to pi over 3. So we still have to find this antiderivative. So we're going to think about what the U substitution could be. All right, and in this case, there's a few different choices we could have here. We could let U equal secant of x, and there'd be some logic to that, because in this case, this is really secant of x squared, with the tangent of x as being multiplied by it. So in some sense, this is the innermost part of this composite function, or this integrand. But that's not the only way to do it. In this case, I'm going to let U equal tangent of x, and the reason that I want to do that is because I recognize that the tangent of x, the derivative of tangent, is secant squared. So I recognize that if I let du equal secant, U equal tangent of x, then du is going to give me secant squared x. This should have a dx there. The differential of U is secant squared x dx. And so that pretty straightforwardly accounts for my entire integrand along with the dx. Right. So what I'm going to do here is I'm going to make that U substitution, so I rewrite this integrand tangent of x secant squared of x dx as U du. So again, the U is the tangent of x, the du is secant squared x dx. Now I'm also going to change my limits of integration. So notice here that the limits of integration here are from x equals 0 to x equals pi over 3. And they kind of match up with the bookend here of dx. So whatever this is, d, whatever the variable is, should match up with the variable that these are defined in. So when I go to a du, and I have a definite integral, I want this to be u equals something and u equals something else as the upper and lower limits. So to do that, I plug the lower limit into whatever I've defined u as. So the tangent of 0 gives me this 0. This right here is the tangent of 0. And then the tangent of pi over 3 is root 3. So now this is u equals 0 and u equals root 3 in the integral of u du. So the limits, the upper and lower limits of this definite integral match up with the differential that is its bookend on the end. And now I'm going to go, okay, well, to find the definite integral of that, it's going to be u squared over 2 integrated from 0 to 3, and I make the easy substitution. Square root of 3 squared is 3, so 3 over 2 minus 0 squared is 0 over 2 is 0, and there my definite integral is 3/2. So notice here when we're doing definite integrals, I make that u substitution, but since I changed the limits of integration, I never substitute the tangent of x back in here. I keep that in terms of u, do the easy antiderivative here, and then make the easy substitution and subtraction there. That's the way to go.